Now, the other reason you might look at foams is in physics we have a real fascination with length scales, and foams are nice for this. You can zoom in on the foam. As I said, it's gas bubbles with thin water films. You typically put various molecules in there as additives, usually soap or other surfactants, but now people are looking at nanoparticles and proteins. This stabilizes the foam. We know a lot about the physics and chemistry of that. It's very well understood, okay? But everything in here is in a fluid state. It's a liquid. It flows, okay, liquid or gas. Then you start talking about the next length scale. We call it the mesoscopic scale, the films or the bubbles. Maybe things change. Then ultimately you have the entire foam, and it has these properties that it can act like a solid suddenly. Okay? So we have this challenge, okay, that, and this is a quote I like to use. It's from Landau and Lifshitz, which is a very famous series of textbooks in physics. Although the motion of systems with a very large number of degrees of freedom obeys the same laws of mechanics as that of systems consisting of a small number of particles, the existence of many degrees of freedom results in laws of nature of a different kind. What does this really mean? It sounds fancy. What it means, I like to give the example of entropy. You get a lot of particles together, and we talk about the second law of thermodynamics and entropy. If you're not familiar with it, if you know any teenagers, it's their bedroom. Okay? If you don't do any work to a system, it goes to maximum disorder. That's a teenager's bedroom. Okay? That's entropy. It's a fundamental principle that's related only to large numbers of particles. If I have one atom and I study its fundamental properties and I do my particle physics on it and learn all about the quarks, I don't learn about entropy. Okay? I need to study many particles together. I need that largest length scale of the bubbles. Okay? And so we have my fake two molecules here, my solid and my fluid. Which is which? You're left or right? Is left the solid or the fluid? And is right the solid or the fluid? Okay, so see, this is what happens when I teach. None of the students answer me either. We all recognized immediately solid, fluid, right? Fluids, we know the molecules are all disordered. They move around quickly. They're random. Solid, more ordered, crystalline. Okay, and we know this, and we have a principle that tells us this. This is what I mean by fundamental principle. We're minimizing a free energy. There is a competition between this thing I called entropy, the desire to be disordered, and minimizing your energy, which often leads to something very ordered. Okay, and what makes it interesting, if it was just that competition, it might actually be boring. What makes it interesting is entropy gets to have a factor of temperature. And so as you change temperature, it gets to become more important. Okay, and you get a phase transition. You get to go from the solid to the fluid because now entropy wins, and eventually to a gas. Okay, my foam is going to flow at some point and be a solid at some point, but entropy is not relevant here. Temperature isn't relevant. If I make my shaving cream, it just sits there. It might as well be at zero temperature for all practical purposes. So what is doing this phase transition is our interest. And so what I'm going to do now is move to my demonstrations. Okay. And so we're going to start thinking about things like solids are things that hold their shape. So I have a chunk of aluminum. It's fine. It just holds its shape. It doesn't do anything interesting. And then there's a whole bunch of other more technical things we can talk about. Their stress is proportional to strain. So that just means if I try and stretch it, the more I stretch it, the more force I need. Okay? So the forces have to do with how I stretch it like a spring. They support a shear stress. So that means kind of if I have it on a slant and gravity pulls down on it, it's not going to deform in any noticeable way. It still holds its shape. Okay? And this is the really technical one. They oscillate in phase with the driving. Okay? This is just a fancy way of saying if I start vibrating and forcing one edge to move, the whole solid moves with it in phase. And I'm going to actually show you a picture of that later. Okay? In contrast, we'll put up the first one for fluids. Fluids take the shape of their container. So demonstration number one is I have sand in here that I'm going to pour. Now sand is a solid. All the particles in there are solid, but because we're in a complex fluid phase with particles, I can make it flow. Not only can I make it flow, it doesn't support shear stress. I can pull my tube out. Okay, there was no force on it there. Now I'm going to flow it again. And what I'm going to do is just tap it. If you're near the front, you may have noticed the sand level went down just a little. Okay. I put energy in, and I made it a solid. I can now support shear stresses. Okay. It's holding it up by the tube. Notice this is kind of incredible if you think about it, because I put energy in and I made it go from a fluid to a solid. Okay. Normally if we heat things up and put energy in, we go the other way. Okay. What is the principle? What things are competing? What is the fundamental thing controlling that? Okay, that is the question we ask.